The purpose of this lecture, and we're going to try to keep it short, is just to apply the calculus you've already learned to the equation for the position of a simple harmonic oscillator that we've been talking about. So here is that equation. X, or the position of a simple harmonic oscillator, is equal to its amplitude times either sine or cosine, doesn't matter, of omega t plus phi. So what I want to do is try to find the corresponding velocity versus time function. Well, how do we do that? It's just a position function. All I need you to do now is take the derivative. So please pause and try to take the derivative of this expression. The first thing to kind of pay attention to is what kind of calculus needs to be applied. This is a chain rule problem. So what we have is an operator sine and then another function omega t plus phi. So what we need to do is take the derivative of the inside, which is everything in parentheses here, times the derivative of the outside. So first the derivative of the inside. So omega t, omega in this case is a constant and t is the variable. So the derivative of it is just omega. And phi is a constant, so its derivative is 0. Everything on the inside's derivative is omega. That then gets multiplied by the derivative of the outside, or a sine of the argument. So the sine of anything's cosine, oh, I kind of screwed that up. The sine of anything's derivative is cosine. You knew that anyway. But we do have to remember that the a is still present. So the derivative of the inside was omega once again, and so that gets multiplied by the a that was still there, leaving omega a cosine of the same argument as before. What I want to do now is take a closer look at this expression for velocity. Okay, so let's think about what the graph of velocity versus time would look like for a simple harmonic oscillator. For starters, what would be the meaning of the amplitude of the graph? And I don't mean the word amplitude like capital A, maximum displacement from equilibrium. I just mean the amplitude of the velocity time graph. And then what is an expression that gives us that amplitude? Pause now and see if you can find these. The physical meaning of the amplitude would be the farthest value from the x-axis that the function ever achieves, or the maximum velocity in magnitude. Or you could sort of say the fastest speed, which remember means the magnitude of velocity. Speed is a scalar, velocity is a vector. And that gives us the fastest you're ever going at any moment. An expression for it, well, it's the same idea as when we did position versus time. Remember how in the previous equation, the x equals a sine, blah, blah, blah. It was just the thing in front of sine that gave us the maximum of the graph. So a, or amplitude, was the maximum value on a position versus time graph. The same idea holds. So whatever's in front of the trig function, the coefficient here, is the maximum. So it's positive or negative omega a, and I just use plus or minus because it's achieved twice, once in each direction. So we've already done all this. Let's get rid of that. We could now look at the acceleration versus time function that would correspond. So once again, pause the video and take another derivative. Same process as before. Your inside argument is the same, so its derivative is still omega. And now we just multiply it by the new coefficient out front. So we get omega times omega, or omega squared a. And then cosine's derivative is negative sine, so we end up with negative omega squared a sine of omega t plus phi. So the same two questions we've done on the other graphs. Find the physical meaning of the amplitude of the graph. Again, I don't mean maximum displacement from equilibrium. Amplitude of this graph. And also write an expression for that amplitude. Pause and resume when you're ready. So your physical meaning is just going to be the largest or smallest value of acceleration. And it's achieved, as always, once in each direction, one positive acceleration and one negative, but they are equal in magnitude. An expression for it, you see the same pattern apply every time. Whatever is the constant in front of the trigonometric function in the equation. So here's the trig function sine. What's in front of it? Omega squared a. Well, really negative, but it's not going to matter because I'm going to put a plus or minus here anyway. So if I ask you on a question like, hey, what's the largest acceleration this thing ever achieves? This is how you find it, omega squared a. Let's just summarize the old and new equations. Position of an object moving in simple harmonic motion as a function of time is given here. The maximum displacement, which is the capital A amplitude, is just capital A. Velocity is the derivative of position. This is the expression that we derived. Maximum velocity is the coefficient in front of cosine, or omega A, or A omega, it doesn't matter either way. Acceleration as a function of time, that's the derivative of velocity. Here's what we came up with. And maximum acceleration is going to be the coefficient in front of the sine here. And as always, I use plus or minus because it can be achieved the same in magnitude, but two different directions, so two different signs are possible. The last thing I want to look at, here's the acceleration versus time function again. You may have already noticed this, but if not, there's something in here that, a very large portion of it actually, that has already been defined as something else. And I would like you to pause the video and try to find something in this acceleration function that has already been defined as another term in this unit. Do you see it? So what we have is a sine omega t plus phi, and that's already been defined as x. That is just the position versus time expression from the very first video. So what we can do is just replace this whole boxed green thing with x. And why is that useful? Well, because now if you're asked to find the acceleration of something but you don't know what time you're looking at, you can find it if you just know the position. So if I say what's the acceleration at a certain position, this is the equation you should use. Let's just add that to our summary. Doesn't really fit here. I mean, it's not at any time t, like it says, but it's really at any position x. And so it's useful, like I said on the last slide, because you don't need to know time to find it. That's it. So what I would recommend is that you either write these equations down and what they mean, or take a picture of this, because in the next video you're going to want to refer to these equations to solve a bunch of practice problems.